We're finally finished looking at our common emitter circuit, so now we're going to move on and look at a different configuration, our common collector amplifier. And so as we'll see later, this is oftentimes referred to as an emitter follower amplifier as well. So we're going to consider this simple circuit here. And so a couple things to note which makes this a common collector configuration is one, we see our collector is connected to VCC directly. So you might be saying, well, that's not ground. But remember, our DC source is signal ground. So because our collector is connected to signal ground, we say we have a common collector configuration. We still have our input signal VS connected indirectly to our base, and we also have our output now coming off of our emitter terminal. So all three of these things together tell us that we have a common collector configuration. So let's see if we can find an expression for our small signal voltage gain. So we want to investigate small signal voltage gain the same way as we did with our common emitter circuit. So of course, if we want to do that, we're going to look at our small signal equivalent circuit. So as always, when we're looking at our small signal equivalent circuit, we can start with our three terminals of our transistor, so our base, our emitter, and our collector. So base, collector, emitter, and let's fill in what we know is in between them based on our hybrid pi model. So actually let me move my collector terminal a little further over because we're going to consider our early effects, so we're going to include our output resistance R naught. So between our base and the emitter, we just have our R pi resistance. So this is going to be R pi, and it has some voltage V pi across it. And we know that current through that resistor is going to be IB. Between our collector and emitter, if we're considering our early effect, we have a dependent source as well as a resistor between our collector and emitter. So we get something that looks like this, where this dependent source is beta IB. And of course, again, as I said, IB is just this current here. And our small signal output resistance R naught is defined there. Okay, so this is what's going on sort of inside our transistor. So now we want to connect the rest of our circuit. So by definition, as we said, our collector is at signal ground, so we can go ahead and just connect this to our signal ground. We have on our emitter side, we have an emitter resistor, RE, which connects the emitter to ground. So we can go ahead and include that as well. So we get something that looks like this, so that's our RE. And now we just need to look at our base side. So again, we have this voltage divider biasing. So from our base, we have R1 going to VCC, but remember that's signal ground. And we have from our base, R2 going to actual ground. So both of those are going to be ground in our AC small signal equivalent circuit. So we can say we have this parallel combination of R1 and R2, which is between our base and ground. So this will be R1 parallel R2. And then we also have our coupling capacitor, which remember is going to behave like a short circuit for AC, so we're just going to treat that like a short. We then have RS and finally our VS connected between our base and ground. So we just have a voltage source VS here and some resistance, source resistance RS. So we get something that looks like this. All right. And so it's a little more complicated, and so let me go ahead and label our output voltage as across that emitter resistor. So not quite as clean as we saw for our common emitter circuit, but we can kind of fix that if we just put these two grounds in the same place. So essentially what we want to do is we want to take this part here and we want to flip it down so that those grounds are in the same place. So now our beta IB is going to be sort of pointing up. Our R naught, of course, is a resistor, so it doesn't really matter, but we're bringing that collector down to our ground terminal shown here. With our R pi, what we can do is we can sort of think of, right now we have something that looks like this, and so what we can do is just stretch that out such that we just have a straight line with R pi between our beta and our E. So sort of putting all of that together, so let me put that back in there. Putting all of that together, we can rewrite our circuit into something that looks like this. So again, I've just sort of moved my C terminal down. My E is then sort of at the top right, and my beta, I've just sort of moved that down into the left so that that R pi is a straight horizontal line instead of having that little right angle turn. So now we have our small signal equivalent circuit that looks like this. Well, if we're investigating our small signal voltage gain, we can define some variables to help us out with that. So let's go ahead and define a few things. So like we saw with the previous common emitter analysis, it's useful to define some input voltage. So let's call this Vn. And so our Vn, and so I do want to have that as In to be consistent with the notes, is basically our input voltage to the amplifier itself. So remember, this Rs is some internal resistance of our source. So our Vn is the input to the amplifier. And so in order to define that, what we can do is we can talk about some input resistance to our amplifier. So we can say, looking into the base of our amplifier, we're going to have some input resistance Ri. And so to make that a little bit easier, we can also define some input resistance Rib, looking in at this point here. So if we have those things defined, what we can then do is what we saw before is from the resistance reflection rule, we're going to have our Re, and in this case also our R naught, sort of being reflected over to the other side and multiplied by beta. So resistance reflection rule. So we're not going to go into the details of showing that again, but basically using that same principle, we know that the Rib is going to be the R pi plus quantity of 1 plus beta times, and before we just had Re, but now we also have this R naught resistor over here on sort of the output side. So we're going to have the parallel combination of R naught and Re. So that's our Rib. So then we can say the input resistance for our transistor configuration with this with this voltage divider biasing is just equal to R1 parallel R2 in parallel with that Rib. All right. And so we're not going to go through all of the analysis again, but using some standard analysis that we saw with the common emitter circuit, what we arrive at is a voltage gain, a small signal voltage gain, which is equal to our output voltage over our input voltage Vs. And we have sort of two big fractions here. So in the denominator, we have R pi plus 1 plus beta times that parallel combination of R naught and Re. And in the numerator, we have the same thing, just minus that R pi term. So we have 1 plus beta times the parallel combination of R naught and Re. And then we also have that term that comes from our voltage divider on the input side over here, which is going to be our Ri divided by Ri plus Rs. And so if you want to see some details about how to do that analysis, you can look in the textbook on pages 421 to 422. Again, it's pretty similar to what we saw for our common emitter circuit. Another thing to keep in mind is that this voltage gain equation is for this particular circuit configuration. If we add some resistors or change the configuration somehow, we would need to rederive an equation. So looking at this expression, we can note a couple of things. So again, typically we're going to assume that our Ri is relatively large, such that this term over here is going to be about 1. Looking at the first sort of fraction, we can see that it's essentially the same. We just have this R pi term here. And so what we can say then is that this fraction here out front is also going to be approximately 1. But it's going to be a little bit below because we do have that R pi in the denominator. Same thing over here. This is going to be approximately 1, but a little less than 1 because we have that internal source resistance Rs. So AV, then we can say for our common collector configuration, is going to be close, but just below unity. So just below a positive 1. And so that's the other thing to note too, is that this gain is positive. It's not negative as we saw for our common emitter configuration. And so for some typical values, we could look at example 6.12, which is on page 422, and plugging in values for sort of the values we had in the circuit above. I didn't point them out explicitly, but we have 50K for R1 and R2 and 2K for Re. What we get is we would get a small signal voltage gain AV, which is approximately 0.962. So as we see, sort of as we expect, it's close to 1, but just below 1. One other thing about our naming then is we noted that our output voltage is equal to our emitter voltage in the initial circuit. And so what this means then is because our gain is 1, then our emitter voltage is following the input voltage. So emitter voltage follows our input voltage. And so the reason we say it's following the input voltage is, again, because our small signal voltage gain is about 1. And so that's where we get the name emitter follower. So oftentimes you'll hear this configuration referred to as emitter follower as opposed to common collector. So the big question then becomes, why or how is this useful? So our voltage gain is 1, big deal. Why do we even need to do that? And so that's a very good question to ask. And so in order to answer that, in the next couple videos, we're going to consider some other characteristics of this configuration. The first one being the output resistance, and the second one being the small signal current gain.